everyone. In the previous class, we discussed about the elastic analysis of the circular tunnels, and we saw that how various components of the stresses like radial, tangential and the shear stresses can be determined along with the displacements, that is the radial displacement and the tangential displacements. We also saw their variation all along the tunnel periphery. Now, note that we did not have any lining in case of the circular tunnel in that earlier class, but then let us say that if we have the thick concrete lining for the circular tunnel, so in that case the question is whether it is possible to carry out the elastic analysis for that. So, the answer is yes. We have the theory related to thick wall cylinder in the theory of elasticity, and by making the use of this we can address the problem of thick concrete lining in case of the circular tunnel. So, how this is done? See here that the problem of concrete lining of the tunnel. So, how this is done is that, take a look here, that the problem of concrete lining of the tunnel can be addressed by considering it as a thick walled cylinder under uniform internal and external pressure. So, this has been shown here with the help of this figure that it is the thick walled cylinder with this as the thickness of this cylinder. This is subjected to an internal pressure Pi and an external pressure Po. And you can see that I have put a negative sign representing the compressive nature of these pressures. The internal radius is A and the external radius is B, and the angle theta I am measuring in this direction from the horizontal axis. Any point here can be represented by the coordinate r comma theta. So, first let us take a look at what are going to be the boundary conditions for these. So, we have here sigma r at r equal to A, this is going to be minus Pi, and tau r theta at r equal to A will be equal to 0. Now, what about the outer periphery? So, we have sigma r at r is equal to B is equal to minus Po, and tau r theta at r equal to B, this will be equal to 0. So, in a combined manner, mark these equations as equations number 1. So, here negative sign indicates the compression. So, how should we approach here? So, these boundary stresses we saw that they are independent of theta. So, we can say that the Airy's stress function phi, which will represent this type of problem, can be the function of r only and not the function of theta. So, accordingly, this phi can be assumed to be a r square plus c log r, where a and c are the constants which will be determined from the boundary conditions. So, let us try to write the equations of stresses in terms of phi. Then we will have this sigma r as 1 upon r del phi del r plus 1 upon r square del 2 phi del theta 2. So, just differentiate this equation number 2 with respect to r and c. This you will get 2ar plus c upon r, and since this phi is independent of theta, this term will be equal to 0. So, all we will have is 2a plus c upon r square. Make this equation as equation 3a. Then we have sigma theta, that is equal to del 2 phi del r2, or we can write it as del r of 2ar plus c upon r, and this will become 2a minus c upon r square. So, this is equation 3b, and then finally, we have the expression for tau r theta, and this will be equal to 1 upon r square del phi del theta minus 1 upon r del 2 phi del r del theta. Since here in both the terms you have the derivative with respect to theta, so this will be equal to 0. So, this equation I will write as 3c. Now, let us substitute these boundary conditions and see how we can go ahead with the derivation. So, what we have is that r equal to a, your sigma r is 2a plus c upon a square, and we have seen that this is equal to minus pi, and we have tau r theta to be equal to 0. So, I write these equations as 4a and b. So, this equation is 4a and this equation as 4b. Then we have at r is equal to b, sigma r will be equal to 2a plus c upon b square, and this is equal to minus po, which is the external pressure, and we have tau r theta to be equal to 0. Mark this equations as 5a and 5b. Now, from these two equations, if you just subtract, see what you will get, this 2a and 2a will get cancelled out. So, what you will have here is c 1 upon a square minus 1 upon b square, that is equal to P naught minus Pi. This minus minus will become plus here, and therefore, you can have the constant C as a square b square P naught minus Pi divided by b square minus a square. Mark it as equation 6a. Now, once I obtain the expression for C from this 6a, just substitute it in either 4a or 5a. So, you will be able to get the expression for a. So, let us say that I put it in 4a. So, that is going to be 2a plus c upon a square. So, that will become b square into P naught minus Pi divided by b square minus a square, and this will be equal to minus Pi. Okay, and we will get a as half minus Pi minus b square into P naught minus Pi divided by b square minus a square. Okay, or we can write a as 1 upon 2 b square minus a square, and see here what you will get is minus Pi b square plus Pi a square minus P naught b square plus Pi b square. So, you see this and this will get cancelled out, and finally, what you will get a as a square Pi minus b square P naught divided by 2 times b square minus a square. So, this will be equation number 6b. So, this is how we can derive these two constants a and c. Now, what we do is we substitute this back to the expression for the stresses. So, substituting this in equations 3a, 3b and 3c, what we are going to get is sigma r as a square pi minus b square p naught divided by 2 times b square minus a square into 2 plus 1 upon r square a square b square p naught minus pi divided by b square minus a square. So, what you are going to get is a square pi minus b square p naught divided by b square minus a square plus 1 upon r square a square b square p naught minus pi divided by b square minus a square. This equation will be 7a. Similarly, we can determine sigma theta. So, that is going to be a square pi minus b square p naught divided by b square minus a square minus 1 upon r square, that is a square b square p naught minus pi divided by b square minus a square. So, this is going to be 7b. And of course, my tau r theta is going to be equal to 0. So, this is equation 7c. Now, this sigma r and sigma theta, they are also the principal stresses. Why? Since tau r theta is equal to 0. See here, this is equal to 0. So, these will also be the principal stresses. Now, for the design of the lining, the critical loading condition will be when this internal pressure is equal to 0. So, let us substitute this pi to be equal to 0 in our earlier expressions. So, what we will get is sigma r will be equal to minus b square p naught divided by b square minus a square plus 1 upon r square a square b square p naught divided by b square minus a square. And sigma theta will be minus b square p naught divided by b square minus a square minus 1 upon r square, and you will have a square b square p naught divided by b square minus a square. This is equation number 8b. Now, what happens at the inner periphery of lining? So, at inner periphery of the lining. So, what will be the value of r? This will be a. So, sigma r will be equal to, so just substitute r to be equal to a in these two expressions and see what we get is, see, b square with a negative sign p naught upon b square minus a square plus so a square here, that will get cancelled out. So, b square by p naught upon b square minus a square, and this will become equal to 0. And sigma theta will be equal to, just substitute here. So, this r square which will become a square and a square will get cancelled out. So, ultimately what you will have is minus 2b square p naught divided by b square minus a square. Okay. Now, what will happen at the outer periphery when r is equal to b? So, I have this sigma r that will become equal to minus p naught, and sigma theta will be minus p naught upon b square minus a square, and then we have b square plus a square. Okay. So, at r is equal to b, we have sigma r upon minus p naught to be equal to 1. Now, here again negative sign is representing the compressive nature of the stress, and sigma theta will be given by this expression. Okay. So, let us say I take, say for example, B by A to be equal to say 1.25. So, what will happen at R is equal to A, my sigma theta upon minus P naught will work out to be 5.6. You can just substitute the value of B by A in these expression and you will be able to get this term 5.6, and at R is equal to B, what you will have as sigma theta upon minus P naught as 4.5. So, let us try to plot this and try to see the variation of it. So, let me plot it here for you. So, on the x axis I have R upon A, that is going to be representing lining thickness. Okay, and on y axis let us have sigma upon P naught, which is the stress concentration factor. You recall I mentioned to you that how we were defining the stress concentration factor exactly on the similar manner, that is the stress divided by the external pressure in this case, and in earlier case we had that as in situ stresses. So, B by A equal to 1.25. So, let us say I write it this point as maybe 1.25 and here this point is 1. So, basically this will represent R equal to A and this point will represent R is equal to B. So, I just draw a vertical line. So, what did we see, that theta sigma theta was 5.6 at R is equal to A. So, let us first try to draw the variation for sigma theta. So, say this is starting from 0 and then maybe this is 3. So, roughly I do it 1, 2, then 3, 4, 5 and then 6. Okay, so, we had here as 5.6. So, somewhere here it is going to be so this value is 5.6. Okay, and R is equal to B, when B by A was 1.25, that was 4.5. So, 4.5 is somewhere here. So, I draw another line and then the variation is going to be something like this. So, this is going to be the variation of sigma theta along with the lining thickness. Similarly, if we try to draw the variation for sigma r, so at r equal to A, that was equal to 0, and for r equal to B, that was equal to 1. So, this is how is going to be the variation for sigma r. So, it will approach to kind of 1 at r equal to B. So, this is the variation for sigma r. Now, the question is, here we took the B by A value to be 1.25. What if we vary the values of B by A? Then how this sigma theta upon P naught will vary? Take a look. So, here we have the lining thickness in terms of say B by A. So, I have here 1, then 2, 3, 4, maybe this is 5. And then on this axis I have sigma theta upon P naught, maybe 1, 2, 3, 4, 5, 6 and 7 and so on. Okay. So, basically this will be something like this. One. So, the variation in this case will look like this with reference to the lining thickness, which is B by A. Now, how to determine the displacement? So, this was all about the stresses and their variation. What about the displacements? Take a look. As we know that it is, we are going to get these by integrating the stress displacement equations. So, in case if we have the plane stress situation, so what we have is del u del r as 1 upon E sigma r minus mu times sigma theta. Then we have u upon r plus 1 upon v del theta, which is equal to 1 upon E sigma theta minus mu sigma r, and we have 1 upon r del u del theta plus del v del r minus v upon r, that is equal to 2 times 1 plus mu upon E into tau r theta. And I mark these equations as equation 11a, b and c. Now, in our case, geometry, loading as well as the boundary conditions, these are all symmetrical with respect to theta, and we can therefore say that we have the complete symmetry. And therefore, we can have the tangential displacement, which we represent by V to be equal to 0. Now, if there is not the symmetry in either of these conditions, that is either geometry or loading or boundary, then we cannot say this. So, until and unless there is the complete symmetry, tangential displacement, we cannot say that it will be equal to 0. But in our case, this is what is the situation. So, we can just say that the tangential displacement is going to be equal to 0. Now, what we do is, we know the expression for sigma r and sigma theta, we just substitute it here and then try to integrate this equation. So, here what we are going to have is del u del r as 1 upon E a square p I minus b square p naught divided by b square minus a square plus 1 upon r square a square b square p naught minus p I divided by b square minus a square minus mu upon E, and I have here a square p I minus b square p naught divided by b square minus a square minus 1 upon r square a square b square p naught minus p I divided by b square minus a square. So, this is what we are getting. Now, if I integrating this, what we will get is that u is equal to minus 1 upon E into 1 upon r a square b square p naught minus p I divided by b square minus a square minus mu upon E 1 upon r a square b square p naught minus pi divided by b square minus a square plus 1 upon E a square pi minus b square p naught divided by b square minus a square into r minus mu upon E a square pi minus b square p naught divided by b square minus a square into r. Or if you just simplify this, you will get ultimately as 1 minus mu r a square pi minus b square p naught divided by E times b square minus a square minus 1 plus mu a square b square p naught minus pi divided by E times b square minus a square into r. Make this equation as equation number 12. So, this is how we can find out the displacement u, and due to complete symmetry displacement v, we have seen that it is already equal to 0. Now, for the critical condition, we have pi to be equal to 0. So, our equation 12 reduces to u as minus b square p naught by E b square minus a square into 1 minus mu times r plus a square upon r 1 plus mu. So, this is how we can determine for the critical condition what is going to be the expression for displacement. Now, what will happen at the internal periphery of the tunnel? We have r equal to a. So, just substitute r equal to a here. What you will get is u as minus 2ab square p naught upon E times b square minus a square, and we can write this in the non-dimensional form, that is as if it is u by a will be equal to minus 2b square upon b square minus a square into p naught upon E. So, this is how you can determine the expression for displacement and also for stresses in case of a problem of the concrete lining to the circular tunnels. So, today we learnt about this elastic analysis of the concrete lining for the circular tunnel, and we took the help of the theory of elasticity and the problem of thick walled cylinder to solve the problem. Now, there can be the tunnels which are not circular in shape. So, how can we carry out the analysis of non-circular shape of the tunnels? That we will learn in the next class. Thank you very much.